So word similarity, we can say that it is actually the relationship between two words, and more specifically it is actually the relationship between two senses, right? So the two words may be synonymous or may not be synonymous, and actually the two words are synonymous in terms of their senses. So as an example, the sense 1 of bank is similar to the sense 3 of fund, right? Sense 1 of bank is similar to sense 3 of fund. Similarly, sense 2 of bank is similar to sense 5 of slope, right? So it's very like very vague to say that in lexical semantics or in computational linguistics, it will be not very good to say that word bank is not similar to the word slope, right? It is somewhat it will be vague, because the word is somewhat the bank, some sense of bank is related to the word slope, right? So we need to compute the similarity using some similarity measure between the words and their senses as well. So the word similarity is applicable in lot of applications. In question answering, we need to match the similarity between the words that are appearing in question and the words that are appearing in answers, right? So we need to know in the answer, in the question, which sense of the word is being referred to, or which sense of the word is being asked in the question, whether it is a river bank or whether it is an institutional bank. According to that, the answer must be generated. Similarly, in natural language generation and essay grading is a problem in which there is some kind of essay that is written by some person, and that the quality of that writing is automatically graded with the help of some task that's called as essay grading, and in plagiarism detection. So these are things where we can use the word similarity. So the similar words are actually, they may be some synonyms, they may be near to synonyms, and the words that are similar, they may be related, they may not be related, right? So for example, car and bicycle are similar words because they appear near in the corpus. Similarly, car and gasoline are related with each other, right? But they may not appear in near in the corpus, right? So they may not appear similar when we calculate the similarity. So one is the there are two types of similarity algorithms. We have already seen what are the distributional algorithms or distribution semantic algorithms, in which we use the vectors and we generate the word vectors in order to calculate the similarities. The another one, the next one is the thesaurus based algorithms. So are the words nearby to any other word in the hypernym hierarchy or the wordnet graph? Or second method is that, do these words have similar glosses? So similar glosses means that a particular sense of word is having similar glosses. Now we will again see how we calculate the similarity in glosses by some method. So one method is actually the path based similarity, the first one here, in which we see the nearby in the hypernym hierarchy. So we require a graph that is a hypernym hierarchy. So hypernym hierarchy is, we see that these are all the hypernyms are present here. So the standard, we have this standard and then medium of exchange and currency and all. So these are in a hierarchy of hypernyms, right? So we say that two concepts. So here we have the concept as senses and synsets. Synsets are those words that are synonym of. So this have a word may have multiple synonyms. So we are here right now concerned with the senses and not the synsets here. So the two concepts or the two senses are similar if they are near each other in the thesaurus hierarchy. So in this path based hierarchy or in this hypernym hierarchy, if two senses, that means this nickel and dime, this nickel and dime, suppose these are the two senses of the word coin. So these two are near to each other, that means these two are similar to each other, right? So we can calculate the similarity between the nickel and money as well, and we can calculate the similarity between the dime and the scale, right? So dime is again another kind of measurable thing. So how this path is calculated? So in order to calculate the similarity, we need to calculate the path. So we first calculate the similarity of two concepts by calculating the similarity between the two paths. So the path length is actually the path length is the number of edges between two concepts, C1 and C2. So if we see here, we see the path lengths between nickel and coin is 2. The path lengths between the nickel and richer scale is, we count it 1, 2, 3, 4, 5, 6, 7, right? So we add 1 to all the calculated path lengths, right? So we add 1 to the number of edges between the shortest path in the hypernym graph between the sense nodes C1 and C2, right? So the path length between nickel and richer scale, or let's take some other one, between nickel and currency, nickel and money, is equal to 1 plus, so what is the number of lengths? 1, 2, 3, 4, 5, right? So 1 plus 5, which is 6. So the similarity of path between nickel and money is equal to 1 by 6, that is 0.17, right? So this is one method of calculating the similarity between two concepts, right? Now there is some problem with this because we are actually considering each of these edges as a single count, right? We are not weighting these edges, right? Whether it is money of exchange with medium of exchange with money or currency. So we are giving equal weightage to all the relationships, right? So this may not be necessary in the corpus, right? Some words or some senses have some stronger relationships with the other words, other senses, right? So but we are giving equal weightage to all the relationships. So this method works, but this is not a very good method. So instead of that, we may require some method that may also calculate or that may represent some of these edges with some weights or some probabilities, right? So in this now the information content similarity comes into play. So it is defined as the probability of a randomly selected word in a corpus is an instance of the concept C, right? So it means that for a given corpus, a word observed as a noun is a member of a concept with probability PC, right? So if there is a corpus and there is a concept, right? This is the corpus and this is the concept, and there is a member of that concept, some word that is a member of that concept. So if that is a noun, so this noun is is a member of the concept with probability C, and if it is not member of that concept, it is having the probability 1 minus PC. So this is C1, this is N A, and there is some other concept. Like this C2. So in this way, this NA is actually having the probability of P of C with concept C, and if there is another concept C3, it is not a member, though the probability is 1 minus PC. We will see how we will calculate these PC probabilities. So this is the PC can be calculated as the count of all the words divided by the total counts, right? So what we define here is that we define the words of a concept as words of a concept are the children of that particular node in the graph, right? So the word natural elevation has the words as hill and ridge, right? So natural elevation is a concept, and the nouns are or the words are hill and ridge. Similarly, we have the words geoformation. So this geoformation is having hill, ridge, grotto, coast, cave, shore, and natural elevation, right? So all these are the words of geoinformation. So in a corpus, for a given corpus, so we count the frequency, right? We count the frequency of all these, like we count the frequency of this and something like this, right? Then probability of the concept natural elevation, right? So the probability of the concept P of natural elevation is equal to the count of hill plus the count of ridge, that is 10 plus 21 divided by the total number of, suppose the total number of is 1000 here or 100 in the corpus, so it becomes 31 by 100. So this is the probability of natural elevation. Similarly, we can calculate the probability of different concepts. So this, you can see that the probability of all these concepts have been calculated here, right? So entity is having the probability of 0.395, and there may be some other concepts present above entity also, so that may be representing the other probabilities higher than entity. We see that as we are moving from leaf towards the root, the probability is increasing, right? Because we see here that the total number of count of words is also increasing, right? So for geoformation, P of geoformation, so we have the counts of all these, right? So this is 4, 2, 6, 12. 12 plus 10 is 22, 22 plus 21 is 41, and 45 and 53. So this is 53 by 100, right? And when we go to the root, the probability becomes 1. The probability of root is 1 because it is actually root is having the children as words, and the count is of all these words is n, so n by n is 1, right? So in this way we have this information content similarity. We can calculate it with the help of the concept probabilities. So now this information content is defined as minus 2 log p of w, minus log base 2 multiplied by the probability of w. So if I want to find the information content of a word w, it is equal to minus log base 2 probability of w, right? So here this is an example. If p of heads is 0.5, so the information of heads is actually minus log 2.5, right? So this is minus log 2.5 is 1. If the coin is biased and p of heads is 0.8, then we can calculate the information p of heads as minus 0.2 minus log base 2 0.8, so that comes out to be 0.32, right? So we see that here the probability is high, right? So this is low. When the probability is high, then this information content is low. When the probability is low, then information content is high. So what does it mean? It means that with respect to the word similarity, for comparing the probabilities of different words, the word that is having low information content will have higher information in it. Sorry, the word that is having low concept of probability will have higher information in it. So in this graph we see that the word that is having that is at the lower part of the graph, or that is near the leaves, that is having the lowest probability, but that is having highest information. So this hill is having a highest information, right? But this entity or inanimate object is having very low information in it, right? So now information content with respect to a concept can be again defined in the same way, minus log p of concept, and we can also define another measure, that is the lowest common subsumer between two concepts. So which is the lowest common subsumer? So this is again another concept that will be the lowest between the two common subsumers of the concepts. For an example, the lowest common subsumer of hill and coast is geological formation. So we go up in the graph, and then we see where these two paths meet, and that is the lowest common subsumer of the two concepts or two words, right? So the lowest common subsumer of of hill and shore is also geological formation. The lowest common subsumer of hill and natural elevation is natural elevation, right? And of course these natural object and inanimate object entity, these are subsumers, but they are not the lowest one. These are the common subsumers, but these are not the lowest ones. So we use this lowest common subsumer, right, in order to calculate the similarity. So the similarity between two concepts, the Resnick similarity between two concepts is defined as minus log p lowest common subsumer of C1 and C2, right? So the similarity between two words is actually the information between the common information between these two words, right? So the Resnick actually the method actually it's actually the theme behind its method is that the more the words are common, they are more similar, right? So it means that the more common information these words are having, they will be treated as more similar, right? So the more two words have in common, the information in common, the more words are similar. So we can calculate the similarity of Resnick C1 and C2 as minus log base 2 probability of longest common subsumer of C1 and C2. So this is again we can do in the same way. We can have this the probability of LCS hill and coast is the probability of geological formation, right? And we apply the minus log 2 here, minus log 2 minus log 2 of 0.00176, that is equal to 9.1, right? So this is the information content of geological formation, right? So in this way we can calculate the information content between different concepts or words, right? Now Lin also defined the similarity, the difference with little difference between with the similarity of Lin. So actually Lin proposed that the more different are the concepts, the more they are less similar, right? So if the two concepts are having higher differences, they are very less similar, right? So the intention is that similarity between A and B is not just what they have in common, as well as the similarity is also it can also be quantified with the help of differences between A and B, right? So the more differences between the A and B, the less similar they are. So actually he defined the commonality, right? The commonality is actually the information content of common between A and B, and he defined also the difference. The difference between A and B is the information content of description of A and B minus the information content that is common between A and B, right? So this can again be more precisely defined as the similarity between A and B is measured by the ratio between the amount of information needed to state the commonality of A and B and the information needed to fully describe what A and B are, right? So this is not actually, this is directly proportional to. So the similarity of A and B is directly proportional to the information content that is common between A and B and of the information content of the description of A and B, right? So the information content that is common between A and B can be given by the longest common subsumer. So the commonality can be defined by the longest common subsumer of A and B, right? And the description of A and B independent of each other can be defined by the information or simply the log probabilities of P of C1 and C2 or P of A and B, right? So the description of A and B is the description of A plus the description of B, which can be now the description be defined as log probability of C1, and this is log probability of C2, right? Now this actually, the log probabilities are the information. This log P is the information that is common. This is information that is common, and this log P C1 plus log P C2 is actually the information that is having the description of C1 and C2 or A and B, is actually the log of P of C1 dot P of C2. So what is this log P of C1 dot P of C2? It is actually the probability that C1 and C2 are occurring together, right? So the information that is common between the two, the probability of that, the probability of common information between the two to the ratio, the information that is needed to fully describe what A and B are is actually described by the association between A and B, right? So the association between A and B is the count of times the A and B or C1 and C2 are occurring together in the corpus, right? So when we calculate the information content and we apply the information content of on these, so we have minus log base 2, so the minus actually disappears and we get the final formula as this: 2 log P of LCS C1 and C2 divided by log P C1 plus log P C2. So in this way we can calculate the Lin similarity score. Okay, so we see here as an example the similarity between hill and coast is the 2 log P of geological formation, that is the longest common subsumer. This is the longest common subsumer of hill and coast, right? And then we have the log probability of hill, this, and log probability of coast. And so we use all these three in order to calculate the similarity, that is 0.59. And we also calculated the we can also calculate the similarity of wrestling, that is minus log P C1 and C2, right? So that's equal to similarity of Lin is equal to minus log P coast and hill and coast, so that is geoformation. So hill comma coast, so that is equal to minus log geoformation, so that is minus log P of minus log P of geoformation is 0.00176, so that is so that is 9.1. That is 9.1, right? So we can calculate these two similarities in this way. Right, so these methods are the thesaurus based methods in which we use the graph, the hypernym graph. So we require hierarchy graph of concepts or hypernyms for calculation of similarity of Lin or similarity of, sorry, this was the Resnick similarity of Resnick. So this is the Resnick similarity. Okay, so we require the graph or some kind of relationships or hypernym relationships that can be defined between the different concepts in order to calculate the similarity given by Lin and Resnick. So there are some other methods also that do not require this hierarchical graph. Instead, they require the glosses. So we will see those methods. Such methods are called as the Lesk based algorithms, Lesk algorithms, and these are also thesaurus based methods. But so we use actually the glosses, and then we find out how many times the word or the concept appears in those glosses. We will see in more detail in the further classes. So that's all for today.